Docker is a platform that allows developers to package applications and their dependencies into isolated environments called containers. Containers encapsulate everything that an application needs to run, including source code, runtimes, libraries, and settings. This allows your applications to run consistently across different environments. Containers and virtual machines are similar in concept from a development perspective, but they have some key differences under the hood. Containers share the host system's kernel, but run isolated processes in their own environments. They're lightweight and they use less memory because they don't require an entire operating system. Virtual machines, on the other hand, emulate the entire operating system, including the kernel, making them more resource-intensive compared to containers. VMs require a hypervisor to manage multiple VMs on the same host hardware, whereas containers use the host's OS and are managed by a container runtime like Docker. Similar to how the Python interpreter, libraries, and configurations, more concisely known as the Python runtime environment, translate your Python code to instructions that your computer understands, Docker is responsible for providing an environment that allows your containers to run on your host machine's hardware. Docker enhances the portability, isolation, and scalability of your projects. Your application can be deployed in any environment where Docker is supported, so you avoid situations where it works on your machine but not one of your coworkers' machines. Everything within your container runs in its own environment. Different containerized applications can run side by side without stepping on each other's toes. Containers can easily be replicated, distributed, and load balanced across different machines or even clusters of machines. Let's explore a quick example that illustrates why you would use Docker. Let's say that you're building a RESTful API in Python using the Fast API framework. Your development environment is on your laptop, and your app is running inside of a Docker container. Because your app is running inside of a Docker container, it's isolated from the rest of the programs running on your laptop. The containerized application is able to be deployed to a production ECS cluster in AWS whenever it's ready. The production deployment contains the exact same environment as the application did while you were developing it on your laptop. During peak traffic times, you can scale up your application by adding additional replicas or tasks to your ECS cluster, and then scale back down during periods of low usage to save money. Some of the key takeaways from this example are that you have the same application and runtime environments running in both development and production deployments, which means you'll have no more inconsistencies across environments, and if it works on your machine, it will likely work in production. Because your application is containerized and it's able to be easily replicated, you have the ability to scale horizontally in both directions when needed. This makes your application extremely cloud and cluster friendly out of the box. The Docker engine is available for Windows, Mac, and Linux via Docker Desktop. If you head over to Docker's official installation page and click on the link corresponding to your platform, you can follow the installation instructions and you should have a working Docker installation in a minute or two. Now that you've got Docker up and running on your machine, let's talk about some basic Docker terminology. The first thing we'll discuss is Docker images. Images are essentially templates for running containers. They act as a set of instructions used to build a Docker container, and they're a good place to start when starting to learn about Docker. Images are built in layers, which are equivalent to building blocks. Each layer represents an instruction to be executed, such as installing software, adding files, or setting environment variables. Layers are akin to steps in a recipe, yielding a final product resulting from the carrying out of those steps. Under the hood, layers are essentially file system changes that get applied in sequence to form the final image. Each layer is a snapshot of the file system at a specific point during the build process. The next term we're going to discuss is containers. Containers are lightweight, standalone, and executable packages that contain everything needed to run an application. Code, libraries, configurations, and dependencies are all included within Docker containers. Containers share the host system's kernel, which is the core component of an operating system and serves as the main interface between the hardware and software. When you start a Docker container, Docker adds a writable layer on top of the underlying image where all changes like file edits, new files, etc. are stored. Multiple containers can run on the same host and each of them runs in its own isolated space. The last bit of terminology that we'll discuss today is Dockerfile. Dockerfiles are text files that contain instructions for building a Docker image. They define the steps needed to create an image, including references to base images to build upon. Each step in a Docker file is applied to its own corresponding image as a layer. You can find an exhaustive list of Docker terminology on Docker's website in the glossary section. Let's head over to our workstation and run through an example of starting your first Docker container. Let's open up our IDE and run our first container. We'll be running a simple Nginx server that serves a static web page with some text on it. If you look at the files in this project, you'll see that we have just two files, the first of which is a Docker file which describes our Nginx image, and the second is an index.html which we're just going to copy into the web root of the image as we build it. Before we get the container running, let's take a look at Docker Desktop. You can see on the Containers and Images tabs that there are currently no containers or images on my machine. Once we start the process of building the image and running the container, you'll see these sections populate with some data. Let's go back over to our IDE and run some commands. First thing we need to do is turn this Docker file into a usable image. We'll do this using the docker build command. In our terminal, we'll type docker build-t followed by an image name and optional tag, and then followed by the build context, which in our case, since our terminal session is in the same directory as our Docker file, is just the doc character. If you look closely at the output, you'll see each step of the Docker file executing in your terminal, starting with pulling the base image from Docker Hub. Once the build is complete, you'll notice that we now see a row in the Docker Desktop app corresponding to the image that we just built. If you click on the image, you'll see all of the layers that it's comprised of. You'll notice that most of the layers come from the base image from Docker Hub, and the copy instruction where we copied the index.html into the Nginx web root is all the way at the bottom. Similarly, if we run the Docker images command in our terminal, we'll see a single row for the image that we just built. And if we want, we can inspect the image a little further and view the layers that it's comprised of in our terminal by using the docker history command. Now that we have our image ready to go, we can use it to create a container and get our website up and running. To do that, we're going to use the docker run command, and in our terminal, we're going to type docker run -it, which says we want to run a Docker container and we want an interactive terminal attached to it. We are going to specify a container name, which will be Nginx container, and we want to publish port 80 of our host machine to port 80 within the container. And finally, we want to run this container based off of the Nginx server image that we built. When you execute that command in your terminal, you should see a bunch of std out. That's actually coming from inside of the container, and the reason we see that is that we specified the -it flags on the command to run the container. After a few seconds, your Nginx container should be running and listening on port 80. But before we test that, let's head back over to Docker Desktop and see how the Containers tab has changed. You'll notice that there's now a row for our Nginx container with a green box next to it signifying that it's running. You can also see the running status slightly to the right in the status column. If you click on that row, you'll see the same std out that we saw in the terminal when we executed the run command. If you look on the top right, you'll see controls for stopping, starting, restarting, and deleting containers, which can be pretty useful while developing and debugging. If you look along the top of the black window, you'll also see several tabs with different types of information about this container inside of them. Feel free to click through those if you want to know a little bit more about what's going on inside the container. The final thing for us to do is to consume the application running within our container as an end user. Let's open up the Docker Desktop application one last time and head over to the ports column. If you mouse over the value in the ports column for our container, you'll see a URL, and that URL is where our Nginx server should be listening. Let's take that URL and type it into our browser's address bar. You'll notice that browsing to this address causes our Nginx container to serve our index.html to us. If we open up the Docker Desktop application and click on the row corresponding to our Nginx container, we can see that there are some additional rows at the bottom in the std out. If we inspect this one right here, you'll notice that a successful HTTP 200 was logged, and this corresponds to when we typed that address into our browser before.